Good afternoon, everybody. Welcome to this afternoon's webinar. My name's Matt Milton. I'm Editorial and Publications Manager at Timber Development UK. And in a minute, we'll be hearing all about the WorkStack building. And I'll be handing over to Steve Wallis from dRMM, Adrian Campbell of changebuilding, and Alex Brock of B&K Structures. But just before we get started, I'm going to kick things off by telling you all a few things about Timber Development UK. We were formed in 2021 from the merger of the two largest and longest established organisations in the supply chain, the TTF and Trada. We're now the biggest supply chain body in the UK for timber. We span all the way from sawmill to specifier and all points in between. There you can see our three mission statements, and we go about these via webinars like this one, and also by our many publications and our knowledge library. There you can see designTimber, one of our two flagship print magazines. We have designTimber primarily for the design audience, and we also have a sister publication called supplyingTimber for the supply side. You can also see an example of our range of assets in the knowledge library. That's moisture management during construction, which provides essential information on managing moisture during a timber construction. You can also see a good example of one of our knowledge sheets. That's using SIPs. If you visit our knowledge library, you'll find resources on every conceivable timber topic. So dive in there if you'll remember. You can also see a good example of one of our case studies. Our case studies library has hundreds of inspiring examples of timber buildings. That one there is Cotto House, which we'll be presenting a webinar on next month. Many of our resources are free, but a lot of them are member only. So we do encourage you all to join our organisation. It really helps us to put on great events like this one, and upcoming events like our annual UK Timber Design Conference, which we'll be holding in London in July. Just before I hand over to the team behind the WorkStack building, I'm just going to remind you all about the Wood Awards 2025. The deadline for entering your buildings is the 23rd of May. So please go to the Wood Awards website and you'll find out all the details on how to enter. So be sure to do that and don't miss out on the deadline. But right now, I'm going to hand over to Steve from dRMM. So if you would like to start sharing your scene, Steve. Oh, sorry, one more bit of housekeeping. Please, everybody, ask as many questions as you want in the Q&A button. You'll find the Q&A button just towards the bottom of the screen. So do type in your questions there throughout the presentations. Thanks, Steve. Over to you.
Thanks, Matt. Yeah, I'm Steve Wallis from dRMM, and I'll be giving an introduction to the WorkStack project that Adrian Campbell will follow, and Alex from B&K after me. So hopefully there'll be quite an in-depth introduction to our project. The Charlton WorkStack, oops, let me start. Oh yeah, so the Charlton WorkStack is located in Charlton in London. It's quite close to Charlton Railway Station. It's on the southern fringe of the Charlton Riverside Industrial Estate along the Woolwich Road. The area has a long industrial history. It goes back to seafaring ways of the Thames, which was initially marshy land. But as all parts of London, the area is experiencing massive changes, and the area was designated an opportunity area by the Mayor of London in 2008, which has seen a steady shift towards large box retail and residential development in and around the area. And as such, property prices have been increasing. We were approached by our client, the Greenwich Enterprise Board, or GEB, to look at this site. They're a non-profit company that specializes in providing affordable workspace in the Greenwich area. They're an experienced client. They've developed many of their own properties in the past, and they offer light industrial commercial workspace at affordable rates. They what sets them aside, I suppose, as a landlord is that they offer flexible leases without referencing requirements on a first come, first served basis. And that lowers the bar to entry for startup and emerging companies. Roughly 25% of their tenants are from diverse backgrounds, which is significantly more than the London average. GB approached us to look at the site, which is just by the Charlton Football Stadium there, and you can see the Thames Barrier and the Greenwich Peninsula and O2 just off the page to the top left. They needed 14 light industrial units to make sense of the viability for the site, and they would offer light industrial and makers spaces for small and medium enterprises. They wanted the size of the units to vary, and this was a key part of their brief. They wanted tenants to be able to move between units as their businesses grew or constricted. And the budget was tight. So we needed to be super efficient in what we were doing. The materials needed to be robust and long-lasting, and consideration given to things like the loading of goods, movement through the building, and the like. It was a given that we would need to stack the program over several floors while maintaining our site for deliveries and the like. And it was at this initial briefing that our client approached us about using engineered timber, which dRMM has quite a bit of experience. We obviously assembled a team. They included Arup and Adrian from changebuilding on that basis, and then B&K got involved later on. The other key briefing element was that the building was to minimize energy use through natural ventilation, renewable power generation, and meet BREEAM Excellent. So our concept was really to deliver density on the site using engineered timber as a means, and this was the beginning of our WorkStack, I guess, WorkStack concept. The idea, as the diagram on the right, of arranging stories or units within the building and starting to play with the form in an analogy similar to how you might stack logs in a WorkStack, and starting to realize the inherent properties of our timber frame and how we could cantilever elements. The site arrangement is compact. It's a long, narrow site. The Woolwich Road is to the bottom of the page here to the south. Vehicle entry was only allowed through the narrow side on the west. And we needed to allow for one parking space per unit and visitor parking, wheelchair parking, cycle parking, turning, maneuvering for loading. So that took up quite a substantial amount of the site, which really left a small footprint for the building, which you can see on the right-hand side of the site. The concept then was taking this stacked analogy, extracting mass, we were left with the WorkStack form. The advantages of the form as it's seen is utilizing or I suppose shaping the building to create this variable unit size, but also it creates a playful form, it creates diversity in the architectural form, and introduces self-shading to the northwest through the dynamic 6-meter overall projection. It created a building with a smaller ground floor plate than the levels above, so maximizing the site usage and minimizing the embodied carbon through carbon-intensive ground interfaces such as a concrete slab and piled foundations. And this side is a comparison with the business as usual approach of single-story, I suppose, wriggly tin sheds that are common for light industrial developments in the area, where you can see 14 units takes up approximately 12,500 square feet of lettable space, or is 12,000 lettable space, but takes up 19,000 square feet of site, whereas through our stacked arrangement, we're able to minimize that right down to 6,000 square foot, not including parking and the like. So here you can see that stacked arrangement with in building section form. So the ground floor is given over to the logistics of the site, parking, loading bay. There's a vertical spine, and then the units above. And you can see the 1.5 meter cantilever of each story above. The arrangement is to use a steel frame and concrete block infill to the ground floor, and then from the first floor up is all engineered timber. And this was around durability, robustness, and also concerns of potential Thames flooding in the area, so keeping all of the timber out of that zone. You can see the massing model on the left, which is our initial concept, and how we've developed that through working with the design team into the structural model on the right, which clearly shows ground floor of not timber and the structural arrangement of the timber above. So as I said, ground floor is largely given over to the logistics of the site. There's a central loading bay which gives direct access to the circulation core. There's 2 ground floor units that benefit from direct access from the yard. And then a stacked arrangement, all in timber above, where 3 units per floor access directly off the central core. And you can see the progressive cantilever. So quite literally, the units get larger as you go up. The construction methodology in timber was really key to understand, and I'm sure Alex and Adrian will go through that in more detail. But suffice to say that the construction process was very quick, and having done quite a lot of the design work early on, flew together quite nicely. You can see the structural arrangement there in the CLT panels arriving on site and how that started to take shape. And then the superstructure topped out. So the clarity of structural form, where all of the cross-laminated timber creates is structural. It's all creating the structural capacity for the building and also dividing up the units. And you can see the clarity of that architectural form and structure in these images, which leads into the finished item internally. We chose to leave as much of the structure exposed as possible, and it's quite a pared back interior. So hard wearing floor materials, all of the structural timber is left exposed, and then a minimal servicing for the units within. The western facade, which is what you see in the image here, is a combination of polycarbonate panels to the right, ventilated elements in the center, and then glazed pane. And it gives a combination of nice diffused light into the units, the opportunity for natural ventilation and clear views out. And here you can see some of those views and internal shots of the CLT elements. We decided to leave the stair as utilitarian as possible, and it's quite literally a steel grated steel grate tread, I suppose, within the CLT structure, which gives rise to these great views throughout. So quite utilitarian in nature. Externally, it was really important to us that the building celebrated its industrial heritage and the location. It's in proximity to really big industrial, light industrial and warehousing factories or sheds that you see in the background. So we chose a material palette that pulled out that industrious heritage or nature, utilizing corrugated or wriggly tin facade that's broken up by the stainless steel channels at each floor to give a bit of architectural detailing. So that approach wrapped on the 3 sides, and then that western facade utilizing the lightweight polycarbonate and glazed elements creates a differentiation in the carved away side. And it's been really great seeing the building fill up with a number of uses that we could not have possibly anticipated. So the building's fully let, and a few of the uses that are inside include Healthy Bean, who are a workplace customization company. They create uniforms and the like for workplace. Medicine furniture makers who design and create furniture within the space. And this is their studio. And other users such as Cindy, who operates the Korean pantry, making Korean preserves and seasoning within the space. So quite versatile. The other point to note is that the building's, I suppose, very positive in terms of the whole life carbon assessments and energy use intensity assessments that we've undertaken. Since the building's been occupied, we've completed embodied carbon analysis that estimates 271 kilograms of CO2 equivalent per meters in the upfront embodied carbon and 413 CO2 equivalent in the life cycle embodied carbon. This, as the diagrams show, this is significantly below the LETI 2030 office targets for both measures, and substantially less than the business as usual case set out by the REBA. It equates to approximately 65% reduction in body carbon from that in business as usual figure. The diagram on the right is the energy usage intensity, and through the fabric first approach, use of air source heat pump and the minimal servicing of the units, we've managed an energy use intensity of 36.4, which is considerably lower again than the REBA 2030 target for office buildings. So this gives us an A rating when using the LETI embodied carbon declaration target template as here. And the key things for this is really optimization of the building's overall structural design by roughly 40% compared to a more conventional approach. The use of CLT as the primary structure above first floor, which is inherently lower in embodied carbon relative to a more standard approach. I think we benefit from the smaller ground floor, so the ground slab and piles are less in volume than they might have otherwise been. And then also eliminating wall and ceiling finishes and leaving the CLT exposed throughout really helps lower embodied carbon through those follow-on trades. So we're really proud of the design, and at that point, I'll hand over to Adrian to go into a bit more detail on the structure.
Thanks, Steve. Over to you, Adrian. Nice to see questions being answered, so do keep those questions coming. Thanks. Are you okay, Adrian? Yeah.
All good. Well, hello, everybody. My name's Adrian Campbell. I should clarify that I started this project while working for Arup, and it was our friend Ed Clark who retained me as a consultant when I actually left to form changebuilding. So that's good for Ed in extending that collaboration. And important to also note that whilst leading the project, obviously the many others involved, particularly at an early time, Jenny Patterson, and later on lots of heavy lifting by Simon Bateman. So I'll talk on their behalf. I'll mainly deal with structure today. There's lots and lots that could be said about the overall engineering design. And I know there's people probably very interested about fire, and I will touch a little bit upon that, but there's an awful lot to cover in the time. And I thought better to reflect on what we learned about the project, not necessarily a detailed how did we do the project, so hopefully of interest. Second. So if not covered today, I'll just refer you to the TDU case study article on the project, which maybe covers a little bit more than there was other today. I'm going to deal with structural modelling, bits on robustness and the peculiarities of that, some connection detailing, and then design for manufacture and assembly, and a little bit of a follow-up on what Steve had already talked about in terms of embodied carbon, and then hand over to Alex on the construction. So I think it's pretty necessary to actually clarify where CLT, cross-laminated timber, is in terms of codification. So although we've had a history of the development of timber design guides, and there are product standards for cross-laminated timber, there's no standardized design approach, and we're relying very much on first principles theory from academics and working guides. And some of that state of the art is perhaps outlined by a nice one of the cost action studies. But generally, it suggests that when we're using cross-laminated timber, especially in more complex buildings like WorkStack, we need to take extra care and diligence in its application and make sure that the principles that we're using are in line actually with the function of the building. And that's especially true of the changing regulatory environment around fire safety as well. So take some care, I think, is the message that from that. And there's an awful lot of additional background research, consideration of the design approach, which was done for the project. So some of that is about the methods that we commonly use for calculation, and some of those principles are set out in tools. So rather than doing hand calculations, which can be appropriate for many applications of cross-laminated timber, it's quite common for people to use design tools. In this case, we're using the work on CLT Designer by T.U. Gratz, and Alexandra Thiel's work sets out the basic theories for that, but it's quite identifiable that many of the presets in those tools don't actually fit the conditions that we are looking for. So in our case, we've got an industrial use category, which is E, and many of the presets are set to residential work. We have particular issues to do with the duration of loading and forces within wall panels. And early on, we took a very different approach to some of the presets in terms of fire limit state assumptions on charring rates, depths of zero strength layers, glue line delamination, etc. So all of these impact the way that we design using these tools and need to be taken into consideration. Similarly, it's quite common for engineers to use finite element modeling for many applications, and those are very useful. But again, we need to take into consideration the particular material properties and the more brittle nature of wood, especially when we have more complex indeterminate systems. So with Steve and others, we've had previous experience in more complex modeling, both on the Endless Stair and then at Sky Health and Fitness Center, which was around dynamics. So we got used to the kind of orthotropic properties of wood and how to model that accurately within FE systems. But generally, when we're looking here at the stability of the building, we're taking more care about the assumptions on stiffness, which actually then lead to the application of loads in any one direction in any one panel. So our approach here was to acknowledge the nature of wood and look at sensitivity studies in those assumptions when finally determining what loads we apply into the panel designs. It's only a 5-story building, and it was really noticeable that we were required, because of the industrial use, to do a full detailed risk assessment because it's a consequence class 3 building. And this is really unfamiliar territory, especially in timber. But the progressive cantilever, obviously, is, irrespective of that, is sensitive to disproportionate progressive collapse. So we were investigating robustness and key element design, particularly around the leading edge where that's most vulnerable. So one of the benefits of the non-wood ground floor is that it can actually accommodate some of the impact forces from vehicle damage to actually protect that leading edge more appropriately. But the key element design was applied mainly to the front of the building, and it raises questions really about some of the inherent methods in approaches for progressive collapse and robustness analysis of 2.25 times the height not really being that appropriate when you have an unjointed wall panel across the entire floor of a building or along the walls of the buildings in the lengths of the unit. So we have an inherent kind of mismatch, I think, at the moment between codified approaches on robustness and actually the requirements that for CLT, and how do we actually handle that. But one of that consequence class 3 risk assessment actually requires us to look in great detail at some aspects of risk up front, and irrespective of its requirements for Part A of the building regulations, it actually forms a very useful process in identifying a variety of risks in the building, including malicious attack. Future climate change came up, construction stage fire and the issues to do with that, and also external fire spread came up. And this was actually pre-Grenfell, and when we were doing this in January 2017. So in my view, it seems a fairly reasonable approach to look at non-combustibility of external fire cladding well in advance of the required changes now as it have come into play. So yeah, one of the lessons for us was that perhaps when looking at more progressive designs, actually undertaking more comprehensive risk assessments as a matter of course, not necessarily just given guided by consequent class requirements, might be something that we should be looking into. So just kind of one other one on robustness is the application of the tying rules. So unlike in precast concrete, where there are quite well-developed guides to the forms of the ties, the allocation of the ties, as seen here in the diagram on the right-hand side, it's less clear actually when it comes to large panelized systems. And that could, so we spent quite a bit of time of identifying the types of the ties that we'd want and the scale of those ties. And in essence, we didn't agree with some of the guides that are out, especially those related to timber, more noted for lightweight timber frame than mass timber design. So we ended up using vertical tying force values in here, which were more consistent with old BS 5268, rather than the Eurocode values, which are actually determined by masonry design and arching forces rather than mass timber. So we were taking judgments on what we thought were appropriate allocations of the ties, and actually the scale of those tie forces consistent with the design. It's not just the design of the panels. Actually, we identified really early on that the connections and the connection forces would have a significant impact on the building delivery, its detailing, and its costs. So this is a very early sketch looking at the allocation of different types of ties across the building. And those are significantly different to the forms of conventional tying using more domestic applications of cross-laminated timber, both at the leading edge, which is kind of where we have very high compression forces, tie-down elements for some of the overturning aspects where there are some small net tensions for instability, and also the robustness tying both vertically and horizontally, and how we would deal with those. So we were looking at very early concepts of those details and how those would be delivered and their impact on the actual sizing of elements. So if I take one of those details, which is the internal platform of one wall sitting on terms of the internal floor panel, we had multiple early concepts thinking about how we would deliver this effectively, both in terms of the strength requirements, the stiffness requirements for the through properties of the cross-laminated timber floors, but also importantly, the fire performance criteria when we have a fully exposed panel with a non-visual connection. So how do we deliver on all of those aspects in the detailing? So we looked at side fixed ties, which we didn't think were easy enough to machine in manufacturing. We looked at inset tension rods, which would be protected by the panels, and then the final connections protected, but we thought that was a little bit difficult to actually install with the needs of large floor pockets to take the elements through. And we ended up more with an approach based on multiple screw joints and inset plates to actually take both the compressive and in-plane shear and lateral shear forces, including the key element design elements. So that's what we then developed up into a tender design. But the important thing, and maybe Alex will touch on this as well, is the development of that original design, which is to be finalized by the contractor, that detailing, but also importantly, the fire evidence, the evidencing of that for the fire state for a full 60-minute REI. And that, so if you look from left to right here, you've got the early tender design, which we proposed and we had used to kind of test the sizing of the elements and the scales of the forces. The manufacturer, in this case B&K's approach to that, which is modified to suit what they think is more easy to fabricate and to install. And then finally, the testing of that and the evidencing of that for the fire limit stage, looking at impacts of sealant, fire sealant for smoke, boarding protection to any of the floor plates, and actually the influence of screw positions in that and their relationship to the charring zone. And that evidence was provided by a fire specialist for the project to do that in detail. And you can see that some of that work presented in the construction, where you don't actually see what you get. The beauty of the end result is the fact that much of this is not exposed at all. So any of the floor plates are underneath in the floor zone, and elements are actually plugged and protected on the screws as well. So lots of work going on, but nothing of that visible. So what I thought I would do was also talk a little bit about the aspects of the delivery here, and take a look back at why cross-laminated timber is a very effective forms of delivery. Steve has also mentioned a little bit about the speed of construction, but I think it's important to recognize the trajectory that we're on here in terms of looking for forms of flexible manufacturing of low carbon buildings rather than just overly standardized ones. So the beauty of here is the application of cross-laminated timber into a beautiful piece of architecture, not just an overly standardized boxy building, which is important. So we should be aiming for customizable manufacture, not just industrialized or standardized or prefabricated systems, which are historically really something of about the 1950s and 60s, not something we should be really aspiring to with digitized systems that we have now. And within that, we can see how it's important to change from perhaps the engineers and designers' idea of engineer to order or design to order, bespoke systems which are often very beautiful, but to some forms of made to order products, which we pull through the system and understand what is available from manufacturers in terms of made products. So that's the approach that we took on the project. It sort of means that we have to work more clearly with an understanding of the production criteria and production requirements of what is available to buy, rather than what necessarily might just be made by a fabricator or a contractor. So it's important for cross-laminated timber, I think, to actually sort of change the procurement route, and maybe Alex might want to talk a little bit about this. We try to engage with the fabricators and the contractors much more early. Typical tender process make that a little bit harder to do, which we need to really change to make the most out of the benefits of off-site manufacturing and cross-laminated timber methods. And so that leads us to kind of an idea of the sort of scale of the panels that we had on the project. So Steve has shown some of the pictures of that already, but it's important to note that there is no one standard CLT panel. There's no magical 2.95 by 13.5 meter long panel. This is a listing of all sorts of panels made from different manufacturers based on a book by Robert Hairstons and Peter Wilson, which I put into kind of the graphic, and it shows the variety of different panels which are available from different manufacturers. And so importantly here, we had triple span floor panels, which are 19.2 meters long, which are really long, can be made by a number of manufacturers, and up to 16 meter long panels for the walls, to actually have unjointed panels within each one of the units to suit some of the robustness tying criteria. So the very large panels, which actually happily went together fairly easily on site, but it does identify some of the logistic properties that we need to be very clear on when designing with this. It was just really good that we were next to a very large road, which made it easy to actually supply and deliver those. But perhaps this is an area where we might actually get benefit out of generative AI, forming ways of optimizing buildings around a variety of different panel systems and dimensions to show what is easily to do. So the struggle that we have currently with cross-laminated timber and the design approach on many projects is not actually specifying the specific manufacturer and the specific panelization of this early enough, which actually means bringing pre-construction advice or specialist contracting advice much earlier into the procurement process, in my view. And I'll leave you on this one. Steve's talked a little bit about embodied carbon and the operational carbon, but important to note just the structural element of this. It's also, within an A rating. So quite importantly, we're meeting very low carbon aspects for when defining the structural only element of that. But just as Steve was noting energy use intensity, we might perhaps start to think a little bit more about the efficiency of the structural system overall. So we were trialing a metric of wood use intensity in this case, about how efficient is this project overall in terms of its design. So in this case, we've had a working number of about 0.33 meters cubed a meter squared, which might relate to some fabricators' kind of estimates of what is normally used on projects. And we're actually starting a research project shortly to actually do more investigation of this. And the other aspect we looked at, which was something like 30,000 screws used on this job, how much metal is in a wooden building. And so we were coming up with what we think might be kind of average fixing rate, similar to a reinforcing rate of about 9 kgs of metal per cubic meter of CLT, which we can apply into early embodied carbon estimates to get a handle on not just the wood content, but the fixing content of that if we come up with standardized metrics. So I hope that's of interest. I'll leave it there and hand over to Alex.
Thank you very much, Adrian, and Steve as well. Some really, really good points there. So my name is Alex Brock, and I am the pre-construction manager at B&K Hybrid Solutions. We were the structural steelwork fabricator and engineered timber specialists that were signed up to deliver this project. And I wanted to use the slide deck that we have here to really take you on that sort of B&K journey, through to site and then through to structural completion as well, touching on some of the points that both Adrian and Steve have mentioned throughout the presentation. And first, it's worth mentioning the sort of scope of works that we delivered. And I wanted to touch on a point that was raised by both Steve and Adrian about this being a light industrial building. We're seeing a lot of interest in the market from large portal frames being converted to engineered timber. Little did we think that the sort of first engineered timber entry into our industrial portfolio would be something like WorkStack, a really complex, really ingenious design, really using CLT to its absolute maximum potential. And I think it's also worthwhile mentioning F. Parkinson, who acted as the principal contractor on the project, arguably one of their first engineered timber entries into the market from them. But it was a really well managed project all the way through. So a big shout out to them for delivering the works. From our perspective, we looked at the structural steel work to the ground floor, which was about 30 tons in total, 9 tons total of structural steel work brackets across the frame, with 705 meters cubed of both non-visual, industrial visual, and residential visual grade CLT across that frame to give those brilliant timber viewpoints across the building. There was about 5 meter cubed worth of glulam in the frame as well, and part of our package included the intumescent coating and the surface better flame treatment as well. So very much a turnkey system for that structural frame. Due to the complexity of the building, and to be honest with you, on all of our projects, we look at the importance of 3D modeling as something that's absolutely paramount. When a new tender comes in, whether it's stage 2, stage 3, or stage 4, we spend the time and resource in modeling these structures. It helps provide confidence in the price from a cost plan perspective, but it gives us a better buildability forecast. It gives us the opportunity to really stress test the connections, to stress test the panels, the delivery routes, and it will help us reduce waste in the future as well, as we're able to introduce penetrations into the CLT in order to have them manufactured in the factory. CLT isn't the easiest of things to machine and manipulate on site. You're much better off doing it in the factory. So having these items detailed early in the program give us the chance to have those manufactured with the machines that are able to do it completely stress-free in the factory. Now, it's already been touched on the sort of complexity of the structural design and the architecture, and I think Adrian mentioned it with the panel lengths and the manufacturer capabilities. Normally, as a specialist, we would like to place one order with one fabricator of engineered timber. On this project, due to the manufacturing complexities, the larger cantilevering floor plates were manufactured and delivered by a company called Hashlacker, whilst the rest of the structure was manufactured by a company called Stora Enso. So there were some complexities with material warranties, etc. But on the whole, it was generally a really, really smooth manufacturing process from both of those. And you can see here a sort of small map of the timber suppliers. The orange arrows are the Stora Enso facilities, the green arrows are the Hashlacker facilities. So we're generally coming from Germany, Austria, and then the Nordic regions as well to deliver that CLT. And I think there's two really pertinent points on this slide. 532 tons of sequestered carbon trapped within that CLT and glulam for the life of the structure, which is a really, really important metric. And the other one is the growback time, just 2 minutes and 35 seconds worth of growback time in European PEFC accredited forests. So that's not worldwide forests, that's not every tree on the planet, that is specifically European PEFC forests. And it will give you an idea of just how renewable and regenerative this material is as a supply. I'm sure many of you on the call will understand the CLT manufacturing processes, but for some of you that don't, it's worthwhile talking through how this is undertaken. Both Hashlacker and Stora Enso offer a very, very similar sort of manufacturing process with sawmills where they're cutting the raw trees down into lamellas, which you can see a pallet of lamellas going through the side there. I think the photo really shows the energy of the CLT being manufactured. It's a very, very hands-on process. After the lamellas have been machined, they're sorted into different visual grades. They're glued together to form large panels, mother panels. They're then machined to length, either with a nested panel or as a full length panel, depending on the size of the structure. It's packaged up, it's put on the back of a lorry, and then it's driven into the UK via the normal shipping routes. So it is very much a hands-off process from a B&K perspective. We're using a supplier network of engineered timber partners to really deliver, procure this. We design, detail the sort of panel layouts and manufacturing side. It's machined off site, and then it's delivered into site. And you might think that having our products manufactured in Europe is going to add significant time into the program. That's actually not the case. We were working to a 22-week design and manufacture lead in here, with some of that concurrent. So some of the CLT manufacture was overlapping detailed design and coordination periods. That gives us a 10-week on-site program installation for the actual frame once delivery started. And then there was a further 6 weeks worth of site treatment for the surface bed of frame. That has to be undertaken once the building is watertight. So it always sits at the end of the program after the CLT and glue lamp's been installed. Now, it was touched on earlier in the presentation about the site constraints. You can see here from a quick Google Earth screenshot that it is a very, very tight site. The boundaries were pretty close. You can see the footprint of the structure in orange there as WorkStack. The site access comes from the left-hand side of the screen, working our way into the floor plate. We then were very lucky to use a neighbouring facilities space to reverse our way back into the structure to allow the lorries to then drive out back onto the road. We did have limited space for material laydown, so working efficiently with the materials was very, very key. Luckily, both of our CLT manufacturers were able to lock the structures for us, so able to install the deliveries as they came. Normally, we would use a telehandler to move materials around the site. Unfortunately, there was just no space on this project, so the crane was doing a lot of the heavy lifting. And I have a video here which will just sort of give you an idea of how the structure was installed. It starts as the structural steelwork is just finishing, and it works its way through that CLT installation. We had 206 panels lifted at approximately 10 lifts per day, with 97 steelwork members at around 24 lifts per day. So it's a very, very efficient structural capability that we have here with these materials. It was installed across a couple of months that are statistically not the best for rainfall. But as the video shows, we were blessed with some very, very sunny days. So moisture management was well managed. We didn't have any issues there with ponding or standing water, using the appropriate methods of managing that. And you can just see how some of the CLT panels are landed and installed there as they progress down the structure. We're using leading edge protection as well to ensure our operatives are safe on the site. With lots of cantilevered open edges, edge protection is very, very important and very key. And there's some photos here that showcase the sort of level of site that we have, sorting the materials out on the floor ready for the next lift. It was a very, very convoluted, very, very energetic site. And this image shows the lifting sequence. So working from the right-hand side across, working our way back across with the CLT panels to start again from that side to keep the crane operational. And from the footprint on the inside, you can see some of the connection details that Adrian was referencing there, everything hidden away where it needs to be. We used a number of temporary propping brackets for the walls here, obviously on a visual surface. So it's very, very key to make sure that these details are repaired afterwards so that the client and the end tenants don't have a load of screw punctured holes in their CLT walls. But it will give you a great idea of, the long span panels for the walls, no jointing details between them, very minimal jointing details between the CLT panels for the floor as well. So it's very, very important to have the long span CLT manufacture. And then transitioned into the finish, we're using a range of different product types here from a residential and industrial perspective, which really gives that unique timber feel to the tenants in the building. It's fantastic that it's been able to be left exposed in such a way where everything is timber is exposed. There's a number of different sort of outlet sockets and radiators that you can see in the photos here, which have to be, but the remainder of the CLT structure is there on show. And I think just finally, it's worth touching on moisture management. It is a growing topic within the CLT industry. With a project like this, where it is heavily involved with CLT, lots of floor plates where moisture could get trapped. It's very, very important to operate what we call a moisture management plan for the delivery. And from our perspective, that's a case of checking the moisture content of the CLT panels when they arrive to site, keeping record of those throughout the duration of the project. Once the CLT is installed, we'll apply a tape between the joints, we'll apply end grain sealant to any exposed end grains, and any water that does find its way onto the project via rain will be wet vacuumed away from the structure to make sure we're taking it away and not just pushing it down to the next level. And those really are the fundamentals of moisture management. It's also, key to continue to take those moisture readings as we progress our way through the structure to understand how the CLT and the glulam are performing from a moisture perspective. And that brings us to an end of the WorkStack presentation. On behalf of Steve, Adrian, and myself, I want to thank you guys for listening today. I hope you've been able to get some insight into the WorkStack structure, and we'd be pleased to take any questions. Thank you.
Thank you, Alex. Yeah, 3 fantastic presentations and a great little video there. Thanks. There've been a number of questions which Steve and Adrian have been valiantly answering. I'm wondering if we should just, even though you've done a very good job of answering these already, Steve, as there were so many questions about the fire strategy, I'm just wondering if you could just recap a couple of things that you've answered in terms of compartmentalization and the like.
Yeah, absolutely. Yeah, it's a good point. Obviously, building out of timber presents a lot of fire-related challenges, and this building was initially designed in the pre-Grenfell context, and then had to, I suppose, be updated just before construction to suit the post-Grenfell context as well. So we've kind of done it twice. The key, I guess, thing to know about the fire strategy is it relies on the units, which are relatively small, providing compartments. So the idea being that if there were ever a fire, it would be contained to one of the units where the fire load is, and not, I guess, as a lot of commercial buildings or industrial buildings are a lot larger, and there's less way of maintaining or condensing fire spread. So that's the key thing. The advantage of that is that the timber would only ever be exposed to fire from one side, and that was a key consideration throughout the design and detailing of the project to make sure that that was the case. And then all the usual, I suppose, checks and balances of making sure products that are specified meet through tested requirements and regulatory standards and the like, which is always a challenge with timber buildings. But as this building attests, it is possible, and there are ways to circle that.
Steve, can I just add to that one? It's really important to recognise that the fire safety strategy is specific to this building, and its design and its location, right? So it's a really important matter, but we can't look to just necessarily standardized solutions. We need to be thinking about each project and the specifics of each project, and there's some interesting questions about use in the building and restrictions. So you mentioned the fact there's no gas. There are certain assumptions about trying to mitigate out some of the risks. There is a non-combustible ground floor which allows for other uses as well, which wouldn't be so sensitive, but yeah, it's a specific one. And the really important bit and the trial for the project and the delivery team was actually evidencing the fire performance through all the panels, all the joints, all of the stopping, all of that being fully evidenced to provide confidence in the fire safety strategy overall.
I noticed as well, Steve, you had made a few other points in the comments that I suppose relate to what you just said, Adrian, about it being specific to that building, that you have a ventilated lobby and a short travel distance to the protected stair, the stair being made of steel.
Yeah, exactly. Those are all considerations, and Adrian said, I think having a fire station 3-minute drive down Woolwich Road was one of the considerations as well. So yeah, I guess it's working with in this case Arup, but a fire engineer to understand the context of the project, the specific nature of what you're proposing, and then coming up with the detail around that. I think that's
yeah. So there's other details which we could touch upon as well. So the external fire flame spread from pluming out the windows, for instance. We didn't have evidence to justify non-combustible cladding and non-combustible insulation providing protection to the external layers of the CLT. So there's a fireboarding all the way on the outside of the building, which is necessary. So unless and until we get the evidencing of that, we're going to have to take protection to the CLT in certain instances where it's necessary. So yeah, it was a really strong thread through the entire project about making sure that we gave, comfort and evidence to all of the work.
Great. So moving on to a completely different question I thought was interesting was asking about the imposed loads when the end users were essentially unknown. I think the person that asked this question pointed out, some of the sort of tools and machinery she'd spotted, in a couple of the pictures. So yeah, I just wondered, how
it's light industrial. We're not talking heavy manufacturing with print works or anything.
Right.
They're light industrial usage, and that just follows conventional. Don't ask me for the code now.
Okay.
PD 66 something or other. So that's 2.5 kilonewtons for the floors, the live loads, and that's suitable for light industrial, actually also for other potential uses in terms of digital type spaces or office type work as well. So there are some alternative uses for it, but it's not heavy industrial with exceedingly heavy machinery, and that's not the requirement for GEB. I don't think you get it up in the lift anyway.
And I suppose all three of you have discussed the sort of low embodied carbon of the project, and I think it was Steve's presentation did a good job breaking that down, I suppose, into see the CLT and the smaller ground floor. So yeah, I mean, do you think that having that sort of smaller ground floor, in terms of embodied carbon, do you think we're going to see more cantilevered office buildings out there that to exploit that smaller ground floor, therefore smaller amount of concrete in the foundations, therefore much lower embodied carbon in future?
I suppose our analysis, so we did the whole life carbon analysis internally and then had that validated by a third party. It was a really good process where we were able to really zoom in on which elements of the building were higher emitting than others. I suppose that comment was more trying to justify how, as a building, we've managed to have such a low embodied carbon. I suppose, I mean, it made sense in this instance. It might not make sense in all instances going forward to kind of shrink the ground plane, but it does, in my mind, make sense of the numbers in that those are the areas where you have higher embodied carbon relative to
so the anomaly of this is the metal in the stair is the big impact, right? So the benefit of the project is one in the timber, but actually the lack of lining materials as well. So if you're taking out all of the lining, you've got all of that finishes and the multiple iterations of those finishes through the building life. That's one thing. There's quite a bit of structure under the ground, especially on the leading cantilever and the scale of the forces. So we were very clear about concrete specification, kind of improvements, design efficiency of the ground beam elements, all those things to design those down in terms of impacts. But yeah, and I've made a comment about the 9 kgs of metal per cubic meter of CLT. So we're also trying to kind of have more thorough assessments of the timber impacts as well, looking at the connections, and we can itemize those out with BIM. I'm sure Alex will know. I've got 30,000 screws in my head for this project. I can't remember how many you might have noted.
I don't think you're far off there, Adrian. There was a question that I'd spotted that had come through regarding the dimentability of the structure, and I was quite keen to get Steve and Adrian's thoughts on this, whether it was considered at the early stages. But with the structure being CLT and predominantly dry construction, yes, in theory, the structure could be taken down from our perspective. It's held together with screws and plates. From an end of life perspective, there's multiple uses for CLT, whether you're able to certify it to be reused in another structure or whether it's able to be recycled into another product. There's a number of different uses. But Steve, Adrian, I mean, was it a consideration for you at design stage to be reused?
Well, I've written a paper on it. You can go and read it. Design for manufacture, assembly and disassembly. So we could also act about adaptation and adaptability in that as well. I have a picture of an advanced deconstruction tool. It's my Stihl chainsaw. So it, you know, the ability to unscrew buildings is not necessarily proven. So there's some evidence that, you know, screw head torque will make that quite difficult, but it's quite easy to actually just take a chainsaw to a timber building and take it apart, to be honest. So we've got really large panels, which actually makes the potential reuse of those a little bit better. So, you know, large unjointed wall panels makes them more easy to apply in other ones. But let's face it, the best thing about intercircularity is the idea of using timber in the first place, consistent with you know, a natural ecology approach, and actually making it last. So actually the durability and adaptability of the building into the long term will be probably more impactful early on. It's very difficult to design for full demountability, disassembly with CLT at the current state. But yeah, chainsaw, that's what I would suggest.
We're a little bit over time, but I will just, you know, I guess, ask all three of you if there's any other questions that you saw that you'd just like to touch on, or any other points that have already been made that you'd like to reiterate or elaborate on.
Yeah, just one, if you will, Matt. There's a very good one from Lucy on how does the building stand up in the lateral direction. So sorry, it's a bit techy. Yes, it's a cross-wall type system. So you've got dominant stability in the long direction of the building. So it requires a very stiff floor diaphragm to take forces laterally back to the rear core area. So one of the determinants of why we wanted an unjointed floor and minimal joints in the floor, the 19.2 meter panel, is actually we wanted to avoid flexibility in the diaphragm. So all the lateral forces are determined by diaphragm stiffness, taking those lateral loads back to some of the cross walls, which are more around the core area of the rear. Hopefully that's okay.
Great. And yeah, I'll repeat what you said earlier. There is a technical case study on the TDUK website. If you go to our site and search on WorkStack building, you should be able to find a case study and read more on it. Okay, well, I think I will wrap things up there. I'm just going to tell everybody about the next webinar in the series, which is going to be on Koto House, a very different building. This is a private house using modular construction on a Hebridean island, consisting of 7 prefabricated timber panels using UK timber. So that will be our next webinar on Wednesday, the 14th of May. So do go to the TDUK site and reserve your webinar spot for that. But I will conclude by saying thanks again to our panel, Adrian, Alex, and Steve. And to everybody, have a great afternoon. Goodbye.
Cheers.